Here's a scenario with multiple moving objects connected by ropes. Our herpetologist has now acquired a shipment of caimans and has given up on pushing the crates and is instead trying to pull them across the floor. Suppose our herpetologist has traction over here, but for simplicity, let's say there's no friction between the crates and the floor over here. So suppose he's pulling in such a way that they all accelerate to the right, and since they're moving as one, they'll all have the same acceleration. Given the masses of the three crates, and given the tension in this first rope here, rope 1, we would like to use the concepts of systems to determine the acceleration and also tension in rope 2 and tension in rope 3. And furthermore, we'd like to rank the three tensions in ropes 1, 2, and 3. Since a rope will break if it's subject to too much tension, ranking the tensions is one way of determining which of the three ropes is most likely to break first. Okay, so our strategy, as always, is to start with the free body diagrams and then pick out some axes. So a free body diagram for crates A, B, and C. Those will look like these here for crates A, B, and C. We're treating these ropes as massless. But if the mass of a rope were not negligible and you had to take it into account, you would just treat each massive rope as like a long, skinny box here. And the rope itself would get its own free body diagram. All right, but in this case, the ropes are massless, so we just have FBDs for the crates. Okay, I think without going any further, we can already rank our three tensions here. Looking just at the FBD for crate A, we see that in order for this crate of asps to accelerate to the right, tension 1 has to be greater than tension 2. Likewise, if we look at crate B, the boas, in order for this crate to accelerate to the right, tension 2 here has to be greater than tension 3, pulling backwards on it. So I think we've got it. Tension 1 is greater than tension 2, and tension 2 is greater than tension 3. We've got our ranking. And note that it didn't matter at all what the masses of the crates were. That ranking is independent of the masses. So it doesn't matter if B is more massive than A or A is more massive than B. The rankings don't depend on the masses at all. And so I'm pointing that out because it's a very common misconception here that the rope attached to the most massive object would have the most tension in it. That's wrong. Rope 3 here actually has the least tension in it because this rope is only responsible for pulling on this one crate here. But rope 2, on the other hand, that one is pulling crates C and B. 2 is pulling both of these to the right, so it has more tension in it than this rope does. And likewise, rope 1, that's responsible for pulling all three crates to the right, so rope 1 has more tension in it than either ropes 2 or 3. Okay, so we've got our rankings. Now, let's go on to look at some Newton's second laws to work out the acceleration and the tensions here. If we do Newton's second law for each one of these three objects based on the free body diagrams, here's N2L for crate A, for crate B, and for crate C. All right, note that it's important now, since we've got Newton's second law for individual objects, and we can also use Newton's second law for systems, it's important to label on the page what kind of Newton's second law you're doing each time. This is going to be for A, so divided by the mass of A, and so on. I would like you now to pause the video and write out Newton's second law for a few different choices of systems here. What if we choose A plus B plus C, all of that to be inside our system? What would N2L for that system look like? Or instead, if we just put A and B in our system, what would N2L for that look like? What would be the external forces? And what would be the form of Newton's second law if A and B were the system? And then what if B and C were the system? If this were our system here, what would N2L look like for that? So pause the video, use what you know about N2L for systems to write out that equation for these three choices of system. Ready? Here's what I've got. Okay, for A plus B plus C, if that's our system, then the only external force is tension 1 here, pulling all three of those to the right. So there's the only external force, divided by the total mass of that system. If A and B are the system, then tension 2 is an internal force, so the external forces are tension 1 and tension 3. So there's tension 1 minus tension 3 over mass of A plus B, if that's our system. And if B plus C is the system, then the only external force is tension 2 right here, because tension 3 would be an internal force. So then Ft2 is the only external force over mass of B plus C here. All right, and so we've got all our possible N2Ls here, and I think looking over them, we can see right here that we have our answer for the acceleration of the whole system. Because when we treat the whole system, the whole combination of blocks like a system, then we've got the acceleration in terms of our four givens right here. And that's an example of this two-step approach that we've been looking at for systems problems. Step 1, use N2L for the whole system to solve for the acceleration of the center of mass. Now, we know they're all moving as one, so all of these accelerations are equal to each other. All these accelerations are the same. Okay, so that was step 1, using N2L for a system to get the acceleration of the center of mass. We've got it. Now, the only thing left to find are these two tensions, tension 2 and tension 3. And our strategy recommends that now we use N2L in step 2 for single object to find one of the internal forces. If this is our system, A plus B plus C, then tension 2 and tension 3 are internal forces in that system. So we want to go to N2L for just one object. So let's look at our N2Ls here. If we want to find, say, I don't know, this one looks the simplest. We could solve this one right here for tension 3. So, using N2L for just this one object, for object C, let's bring that over here. We'll rearrange that to get tension 3 is mass of C times its acceleration. And the acceleration we have already solved for in step 1 right here. That acceleration is this combination of our givens right here. So I can substitute this in for that acceleration right there. So there's a substitution. And then if I just do a little bit of factoring out here and rearranging, we see that tension 3 is this combination of masses times tension 1. And look, we can verify a conclusion we made earlier. Mass C is always going to be less than A plus B plus C, so this is always going to be a number that's less than 1. So therefore, we're showing tension 3 is guaranteed to be less than tension 1, like we ranked earlier. So there we go. We've got tension 3 now. Last thing to find is tension 2. So we can go back to our N2Ls. And our strategy suggests we use N2L for a single object to find tension 2. So I see tension 2 appearing here and here. Looks like we could use either of these equations to solve for tension 2. But in this case, I'm going to deviate from the strategy because looking over here, we see that this equation looks very simple. If we choose B plus C to be our system, if this is our system right here, then this Newton's second law for that system involves tension 2 in a simple way. This I would like to rearrange to get tension 2 by itself. Ft2 is mass B plus mass C times our acceleration. Here is our acceleration that we solved for in step 1, so let's substitute that in here and then rearrange those terms to find how tension 2 relates to tension 1. Here again, note that mass B plus C, that's always going to be less. This numerator is always less than A plus B plus C. So no matter what the masses are, this combination is a number less than 1, so tension 2 is always less than tension 1, again confirming our ranking here. Okay, lastly, I think let's note that since tensions 2 and 3 both depend on tension 1, that suggests that if our herpetologist lets go of the rope here and lets rope 1 go slack, so tension 1 goes to 0, tension 1 goes to 0, then we see that tensions 2 and 3 will also go to 0. So ropes 2 and 3 will go slack if rope 1 goes slack.